Okay, so it's my pleasure to have Gianmichele Blasi. In here, he did his PhD with me in Scuola Normale Superiore, working with Vittorio Giovannetti, Fabio Taddei, and Alessandro Brazio. Then we finished our PhD together, and he moved to Switzerland to work with Geraldine Hack, and where he's still working. So it's a pleasure to have you here, Gianmichele, and the floor is yours.
Thank you. Thank you so much. Thank you for having me, and thank you for giving me the opportunity to present my work, my research. Indeed, my name is Gianmichele Blasi. I did work as a postdoc in the group of Geraldine Hack at the University of Geneva in Switzerland. And today I'm going to present this recent paper that we published a couple of months ago on quantum science and technology. This is a work that I did in collaboration with Geraldine and also with an experimentalist from Scuola Normale Superiore of Pisa, Francesco Giazzotto. You know him very well. As you can guess from the title, this work is about hybrid normal superconducting Aharonov-Bohm quantum thermal device. And apparently this is a quite explosive topic because they closed the campus yesterday before that. Okay. But anyway, before explaining all the silly words in this very complicated title, let me just start by giving you a very brief outline of the contents we were going to see in this presentation. First of all, I will start by setting out the framework in which we're going to move. The framework is that of quantum thermodynamics, analyzed, let's say, on a technological point of view. And more precisely, I will focus on the very young subfield of phase-coherent caloritronics. So we'll explain what is phase-coherent caloritronics, why it is important, what are the main questions and main systems under investigation in this context. Then I'll go through the description and presentation of the actual system under investigation in the work, that, as you can guess, consists of a metallic Aharonov-Bohm ring embedded in a hybrid normal superconducting two-terminal setup. And then I will go through the result that we obtained, and I hope to convince you at the end of this presentation that this system can be really used as a powerful, versatile, and multitasking quantum thermal device. Indeed, this can be used as a thermoelectrical systems, meaning that we can, produce electrical current going around in the system just by applying a thermal gradient. This can work also as a very efficient quantum heat engine, namely as a system that efficiently converts heat current into generated electrical power. And also at the very end of the presentation, I will show that our device can be used as a heat rectifier, meaning that the system can force heat current to preferentially move in one direction. So I guess that we can start by discussing some basics. And I think that a good way to introduce quantum thermodynamics, at least on a technological point of view, is by understanding, first of all, what is the real difference between the traditional and quantum thermoelectrical devices. For the first case, traditional thermoelectrical systems are characterized by typical dimensions which are much larger with respect to the so-called scale of thermalization, which is the distance over which electrons relax toward the local equilibrium. And because such a kind of traditional system has no structure below the scale, one can use a standard method such as the Boltzmann transport equation to compute relevant quantities, for example, heat, energy, and charge currents flowing inside the systems. However, the story is completely different in the case of quantum thermoelectrical systems, which instead are characterized by typical dimensions which are comparable or even smaller with respect to the scale of thermalization. And so for these systems, on that scale, one cannot avoid to deal with the purely quantum features like quantization of energy, superposition, quantum correlation, quantum coherence, and so on and so forth. So I think that, at least on a technological point of view, the goal of quantum thermodynamics is that of using these quantum features in order to possibly improve classical thermodynamical quantities, such as efficiency, electrical power, and charge heat currents, and so on and so forth, And on the other way around, one can use such a kind of classical thermodynamical features in order to describe and characterize a quantum system, but on a thermodynamical perspective. Let me add also that recently a lot of attention has gained also this very young but yet successful field of phase-coherent caloritronics. And here the goal is that to control heat and energy currents flowing in these quantum mesoscopic devices by exploiting one of the most peculiar features in quantum mechanics, which is the quantum dynamical phase of wave functions of electrons scattering in these systems. And in this context, two of the most important and, let's say, paradigmatic systems under investigations are the so-called Aharonov-Bohm ring, which is indeed a metallic ring embedded in a multi-terminal setup. And on the other side, we have also the so-called Josephson junctions, which instead are hybrid systems in which superconducting components are put in contact with other materials. In the first case, in the case of Aharonov-Bohm rings, it has been shown in literature, for example, in these very two last papers by Geraldine and Francesco Giazzotto, that applying an external magnetic field, you can control indeed the phase of electrons scattering inside the ring. And by doing this, you can, create a kind of interferential mechanism inside the system. And by exploiting this interferential mechanism, one can generate thermoelectricity. Namely, you can produce fluxes of charge currents going around simply by applying a thermal gradient between the two rings. And in the same spirit, but in the context of Josephson junction, this is possible also in this kind of hybrid systems. And especially this is possible by exploiting two of the most important characteristics for superconductors. The first important characteristics and features is due to the so-called Andreev reflections, which happens when an electron is coherently reflected back as a whole or vice versa at an interface with a superconductor. And for example, we used this Andreev reflection in a collection of works that I did during my PhD. And we showed that using such a kind of Andreev reflection, you can indeed create Andreev interferometric mechanism inside your junction. And almost in the same fashion as it happens for the Aharonov-Bohm ring, by using this interference, you can create thermoelectricity. And the second and very important characteristics of superconductor is also that they are characterized by an energy gap delta, which depends on temperature. And more specifically, this energy gap, which is just the gap energy between the Cooper pair condensate and the quasi-particle spectrum, is maximal for a very small temperature, and then it closes when passes through this critical temperature. And because of this thermal dependence of the gap, whenever you apply a thermal gradient to your system, you break the left-right symmetry of your system. And doing that, you can force heat current to preferentially go and move in one direction only. And by exploiting this feature, you can realize what is the thermal version of the electrical diodes, actually. So far, I talked about quantum thermodynamics. I explained you this context of phase-coherent caloritronics, pointing out the two of the most important systems there. And from now on, I will explain really my work. I will really deal with the actual system under investigation in my work that really consists in merging these two systems, in putting in contact an Aharonov-Bohm ring with superconducting components. And indeed, the results is the following: an hybrid normal superconducting Aharonov-Bohm device. So, as you can see,
Can I interrupt you for a second?
Sure.
Can you go back to the previous
Sure.
example? So in order to have thermal electricity, you need to have some breaking electron hole symmetry.
Exactly.
You have to have some breaking of left-right symmetry. And so you were alluding to that about the temperature dependence of the gap. But can you kind of just sort of connect the dots? Where does the thermoelectric response come from in this right system?
You're perfectly right. The thermoelectricity comes from the particle asymmetry. Particle asymmetry in the transport domain means that your transmission function is asymmetric with respect to the energy. And you can making this transmission function asymmetric by, in the case of the Aharonov-Bohm ring, by using this magnetic flux. And indeed, you can see that it becomes asymmetric and you have Seebeck coefficient, for example. In the case of Josephson junction, this is possible by playing instead with the Josephson bias, so the superconducting phase difference between the two superconductors. So let's go back to the actual system under investigation. This, I should say, consists in the central part that is really the Aharonov-Bohm ring. It is characterized by this tau parameter, which just corresponds to the transmission probability for a particle to go from the ring to the lead and vice versa. And also we account for the possibility to control the ring through or the application of an external magnetic flux, phi, or through the application of an electrostatic gate potential applied, for example, just on the lower arm. This ring is then embedded between the two leads. To the left, we have a normal metallic ring at the temperature Tn. To the right, instead, we have a superconducting lead with the temperature Ts. Notice also that here we took into account for the possibility of the presence of a contact resistance, which can be parameterized by this Z parameter, which is a kind of a transparency parameter. Namely, when Z is equal to 0, the interface is perfect and ideal, otherwise it is not. So in the middle part of the slide also represented the dispersion relation curves, energy versus momentum of each lead, the normal and the superconducting one. And at this point, it's very important to notice that because we are dealing with superconductors, together with the presence of electrons, we have to take into account also for the presence of holes. And that's why here I represented in solid black lines the dispersion curves for electrons, and in the dashed lines instead, the ones for holes, which are simply obtained by particle symmetry with respect to the electrons. Notice also that in the case of the superconducting lead, the superconductivity indeed opens this gap in the dispersion relation curves, and this mixes electrons and holes, creating quasi-electrons and quasi-holes in the quasi-spectrum. The middle part of the system corresponds to the scattering region, when electrons and holes scatters inside the system, and this region is characterized by its scattering matrix, calligraphic S, that we did obtain by combining the scattering matrix of the Aharonov-Bohm ring, SAB, and the scattering matrix of the interface with superconducting lead, SNS, which is the one that takes into account for the Andreev reflection processes. So these processes that converts electrons into holes and vice versa. So the way we want to characterize the thermodynamical properties of the systems is by using the so-called Landauer-Butticher formalism that indeed allow to compute the charge In and heat Jn currents, for example, flowing to the normal lead. And without entering too much into details of the formula, I just remember that here the square modulus of the scattering matrix corresponds to the transmission probability for electrons and holes to go from one lead to another. The difference of the Fermi function give us information about the occupancy population of electrons and holes in the context. And also here I used the E, which is the charge of the electron, to compute the charge current, and the difference between the energy and the chemical potential to compute the heat. Just I stress here that alpha and beta are just labels for particles and holes. So this is Landauer-Butticher formalism generalized to the case of superconductors, in which you have indeed particles together with holes. Now, the first thing that we want to verify for our system is if it really works as a thermoelectrical device, namely as a system that produces electrical current under the application of thermal gradient. And indeed, we did this. We investigate this property by considering first the so-called linear response regime that happens when delta T, the thermal gradient, and delta V, the electrical bias, are very small with respect to the thermal energy, kV. If this is the case, you can really linearize the Landauer-Butticher currents, And you can express these currents in terms of the so-called Onsager coefficients, L11, L12, L21, and L22, which really corresponds to the electrical conductance, the thermal conductance, and the thermoelectrical coefficients, which are related by the so-called Onsager reciprocal relation. In our case, they are exactly the same. An important figure of merit for thermoelectricity is the so-called Seebeck coefficient. And this Seebeck coefficient is just defined as the ratio between the induced thermal voltage delta V divided by the applied thermal gradient delta T when the charge current through the system is equal to 0. And it's very easy to show that this is related to the Onsager coefficient in the linear response regime by this relation, L12 over L11 times 1 over T. So here I present the results that we obtained for the Seebeck coefficient in the linear response regime. And let's say that in order to single out what's the role of the ring for our system in producing thermoelectrical properties, we distinguished among two different configurations. A first configuration in which we don't have the presence of the ring, so the system is just a normal superconducting Josephson junction, and this is referred to the top panels A and B, and a configuration in which we do take into account for the presence of the ring, in which case the results correspond to the bottom panels. Let me stress also that here for both configuration we consider two different regimes. A regime which is called under approximation, which happens when a delta, the energy gap of the superconductor, is much smaller with respect to the Fermi energy. And we also consider the case in which we go beyond the under approximation. So we relax this limit here. And let me say that it's very important to distinguish between these two different behaviors and different regimes, because usually in literature, there are a lot of papers that just talk about under approximation, but we will understand in a minute that this is not the best situation possible if one is interested in describing the thermoelectrical properties of a system. And indeed, to understand that, let us focus our attention just on panel A, which I remember you just corresponds to a normal superconducting standard Josephson junction without the ring within the under approximation. And as you can see here, the Seebeck coefficient is always equal to 0, independently from the temperature and also for different values of the transparency coefficient. Instead, in order to get a finite Seebeck coefficient, you have to go beyond the under approximation, in which case you see that the Seebeck coefficient is finite and also has this monotonically increasing dependence on both temperature and the transparency. So the very important first take-home message from this slide is that talking about normal superconducting Josephson junction, you cannot obtain thermoelectricity if you are in the under approximation regime. To really describe instead thermoelectricity, you have to go beyond the under approximation, in which case you really can describe the thermoelectrical properties of your system. Now, the story instead completely changes when we do take into account for the presence of the ring, so panel C and panel D, and especially in panel C, meaning within the under approximation, we already obtained a Seebeck coefficient which is finite, and also it can reach orders of magnitudes like hundreds of microvolt per Kelvin. And even better, if you go beyond the under approximation, panel D, we can get Seebeck coefficient of the order of millivolt per Kelvin, which is quite impressive considering that here we are dealing with the superconducting components. So the second take-home message from this slide is that the combination of the Aharonov-Bohm ring with superconducting materials is beneficial for the thermoelectrical properties of the system, even if you're considering the system in the under approximation.
So, just to remember correctly, under approximation would mean the region before which there is no anti-reflection, right?
Under approximation means that you're linearizing your energy with respect to E over delta. So delta over E. So delta is very small, and you're linearizing. And what happens is that your wave number scale, the K there, is just the Fermi K. So if you do this, indeed, what you obtain is that the transmission function is always symmetric in energy, and indeed, the Seebeck coefficient is always equal to 0, independently of the temperature and independently on the other only parameter, which is the transparency there.
So what mechanism does, what mechanism happens that breaks the electron hole symmetry in the panel B?
Indeed. Yeah, actually, because within the under approximation, the only process you can obtain is a perfect under reflection, meaning that an electron is just reflected as a whole, and this is it. In the other case, you have just a mixture. So an electron can be partially reflected back as a whole and partly as an electron. This creates interference. Again, you can make the transmission function not an even function of the energy, and indeed you can obtain finite Seebeck coefficient. This.
One more thing. I was thinking under reflection will happen when the gap is large and then you go and then come back, right?
There are under reflection within the gap and outside the gap, but simply if you are within the gap, it's perfect. If you're outside the gap, it's not perfect in the reflection. This is the only difference.
So here, TC is cold bath temperature, right? Not the critical temperature.
Actually, this is the linear response regime. So delta T doesn't really play a role, and T is within. Actually, I plotted as a function of T over Tc. So let's say that up to 1, you are in the superconducting regime because the gap is open. After 1, instead, is metallic regime. Indeed, if you go for higher temperatures, you approach the metallic behavior of the Seebeck coefficient, which is linear in temperature.
So for T by Tc greater than 1, you basically have N and M.
Indeed, exactly. Perfect. So
one last question. Go back to your previous slide. All right. So what about L12 and L21? So you said that they're equal in the system, but in the second system, you're applying magnetic flux.
Exactly.
So you should break that symmetry.
This has been demonstrated by Buttiger, actually. Yes, indeed, you're right. If you apply a magnetic field, the relation is L21 equal to L12 with a minus B.
With the reverse B.
But actually, it's a peculiarity of the fact that we have a ring that makes again this symmetry again the standard one. So when
accidental symmetry.
Yeah, it's an accidental symmetry, exactly. But this is a very good.
We don't let much pass around here. We're very strict about it.
Yeah, no. You're right. Okay, now the fact that we can obtain such high values of the Seebeck coefficients also inspired us to consider our system as a possible quantum heat engine, namely, indeed, as a system that can convert efficiently heat current into electrically generated power. And in order to investigate this ability for our system, we consider it in the so-called closed circuit configuration. Basically, we attached the terminals of our system to an external load resistance. And also here we consider the case of non-linear response regime. So we are applying a finite thermal gradient. And by applying a finite thermal gradient, the system will respond with a finite thermal voltage delta V. And this thermal voltage can be easily obtained by solving numerically this first equation, which corresponds basically to the Kirchhoff law. So the current inside the normal lead just corresponds to the current passing through the load resistance. And so by solving numerically this equation, you can obtain the thermal voltage, and using the thermal voltage, you can compute, for example, the power dissipated by the system on the external load resistance, which is basically the ratio between delta V squared over RL. And knowing the power, you can also compute the efficiency of your system, which is just the ratio of the power, indeed, and the absorbed heat current Jn. To the left, indeed, I plotted the results for these performance quantifiers. In panel A, we have the power, and in panel B, we have the efficiency normalized with respect to the Carnot efficiency, both as a function of the controlling parameters, namely the magnetic flux, and also the electrostatic gain potential. And here you can notice two important things. The first one is that you really can control these performance quantifiers by just applying and controlling an external parameter, which is very important, at least on an experimental point of view, because this gives you really the possibility to change these thermodynamically important quantities simply acting on a tunable parameter. And the other very important thing here from panel B is that our efficiency can really reach very high values of the order of 55% the Carnot efficiency. And this is much better with respect to the case in which you substitute, for example, the superconducting lead with a metallic one. And indeed, the fact that we can obtain such high values of the efficiency is really because of the presence of the superconductor, and more precisely is because of the under-reflection processes that are happening at interface with superconductor. Indeed, whenever an under-reflection takes place, an electron with energy epsilon is reflected back as a whole with same energy. And what happens is that the superconductor is acting as a kind of mirror for energy flux, meaning that it's blocking the flux of heat current through it. And because the heat current gets smaller and it appears in the denominator of the efficiency gets higher with respect to the case of normal metallic lead. So far so good. And the last thing that I want to talk about is the possibility for our system to be a kind of heat rectifier. As I told you before, heat rectification is that ability of a system to force heat current to move specifically one direction. And in order to verify and investigate such property for our system, we consider it again in two different configurations. A forward configuration, in which the temperature of the normal lead is the hottest, the hotter temperature, and the temperature of the superconductor is the colder one. In this case, you will generate a forward heat current Jn plus going from left to right. And at this point, it's very important to understand that because our system is a thermoelectrical system, whenever we apply a thermal gradient, the system will respond with a thermal voltage, delta V plus in this case. And in order to compute this forward heat current Jn plus, one has to take into account for this thermal voltage, delta V plus. The same happens also in the reverse configuration, in which we instead just swap the temperatures of the two leads, such that the superconductor is now at the hot temperature and the normal one is the colder one. And in this case, we will generate a reverse heat current Jn minus going from right to left. Now, remember that here we are dealing with superconducting lead, meaning that the gap really depends on the temperature of the superconductor. And as you can notice here, the value of the superconducting gap in the forward configuration is bigger because the temperature of the superconductor is smaller, and the opposite happens instead for the reverse configuration, in which case the gap is smaller because the temperature of the superconductor is higher. So here you can really see that we are breaking the left-to-right symmetry just by applying and swapping a thermal gradient across the terminals. And so one expects in general that Jn plus, the forward heat current, to be different with respect to Jn minus, the reverse one. And to quantify this difference, this rectification indeed, we can compute the so-called rectification factor, calligraphic R, which is simply the ratio between Jn plus and Jn minus. If this guy is equal to 1, you don't have rectification. If it's bigger than 1, you have, a Jn plus bigger than Jn minus, and so on. Here I plotted the result for this rectification factor as a function for the hot temperature and for different values of the cold temperature. And indeed, what you can see is that, especially in the case in which T cold is very small, you get a rectification factor which is of the order of 4.5, meaning that the forward heat current is 350% larger than with respect to the reverse heat current. So it's for sure something sizable that you can for sure measure in an experiment. Let's say that as a final result, I want also to stress that also, as the case for the power and the efficiency, we can control this rectification factor by simply controlling the external parameter. And indeed, here I represented the rectification factor as a function of the external magnetic flux. And indeed, you can see that even the quality and also the direction of the rectification can be changed by changing these external parameters. And another important features that I want to describe here is about the relation between rectification and the actual value of the heat current. Because in general, I mean, better is the rectification, smaller is the heat current that you're rectifying. And indeed here I represented in a parametric plot the rectification factor on the vertical axis versus the value of the heat current on the horizontal one. And indeed you can see that the best rectification corresponds to very, very low values of the heat current. But however, you can see here on the right bottom corner that almost for every values of the temperature, we can get a rectification of the order of 1.5, meaning a 50% rectification, which is still good, which corresponds, however, to a value of the heat current of the order of few hundreds of watts. Yes. And if you keep in mind that in standard experiments, you can have access to picowatts, this means that we have a 5 order of magnitude of difference, which is something sizable and that you can measure.
So the axis there is measured in watts?
It's in watt, let's say.
So if I understand correctly, I think the rectification you obtain, not just because of left-right asymmetry, you have to have some kind of symmetry breaking in the middle as well, right? You have to, because if you just have a quantum dot in the middle, and if you just put like different resistance, you never get a rectification because the transmission probability is like a symmetric factor on gamma L and gamma R. You also need some kind of nonlinearity in the system. And in this thing, it looks like either you have to modulate phi or modulate Vg to get that nonlinearity. So like something, because for Vg equals to 0 and phi equals to 0, I don't think you get rectification. Do you?
The curves that we obtain are have been optimized over the parameters to get the best rectification possible. I don't know if you don't obtain rectification for Vg equal to 0 and flux equal to 0. I think you still get rectification because of the non-linearity, not of the system, but of the Fermi functions that describe the leads. And indeed, I want to let me stress this one because it's very important. Thank you for pointing out. Here, indeed, I have two families of curves: the blue ones and the reddish ones. The blue ones corresponds when T cold is smaller than the critical temperature, meaning that you're really exploiting the superconducting nature of the superconductor, while the reddish curves corresponds to the temperature of the cold reservoir, which is bigger than the critical temperature, meaning that you're closing the gap. So you end up effectively with a normal system. So you can say, well, okay, but in the case of a normal system, you don't have the gap. You cannot break left-right symmetry. How is that possible that you get a rectification factor? Well, this can be explained, in practice by Rilling saying that delta V plus for the forward configuration is always different from delta V minus for the reverse configuration. You obtain this just by solving this a couple of equations, basically imposing that the charge current is equal to 0 in the case of the forward and in the case of the reverse configuration. And simply because of the nonlinearity of the Fermi function, solving this numerically, you obtain that delta V plus is different from delta V minus, meaning that you're breaking left-right symmetry not at the level of the gap, but at the level of the thermoelectrical potential, delta V plus and delta V minus. Indeed, you still see rectification even in the normal effective regime.
I think you have to go outside of linear response to make that work, though.
This is totally in the nonlinear response. This is completely...
Even if you go outside of linear response, somehow you need temperature dependence in the transmission probability to get rectification, which I don't see. I mean, if you look for a simple system like a quantum dot or a qubit, then you need to have that temperature dependence of transmission probability gives you the rectification.
Actually,
here I don't see an analogy for that.
Take the simple system possible in which the transmission function of your system is 1.
Yes.
Easy. Your current is still the integral of T times FL minus FR, right? Now consider the forward configuration. So Tn and Ts, perfect, and compute delta V plus numerically.
Yeah, I think that's the reason why you're getting this.
Then swap the temperatures, and you will end up with a different delta V minus that makes the current equal to 0.
Why do you need to calculate delta V plus and delta V minus every time?
Well, because your system
charge current to be 0.
Indeed, your system is an open circuit. So for the current to be equal to 0, you have to compute the heat current at delta V plus.
Okay, yeah, I totally missed that two equations out there.
Yeah, sorry, indeed. Thank you for pointing out. It's very important. As a very final remark, I can say, I mean, we have these two different regimes, the superconducting one and the normal one, right? Depending if the temperature is within or without the critical temperature. However, you can see that really, when you really exploit the superconducting nature of the superconductor, your rectification is the best one. For the normal one, instead, just because this the only breaking or left-right symmetry is due to this thermal power and not because of the gap, then your rectification factor is small, but still is finite, even for the simple system, quantum dot, or even
in this particular configuration. If you suppose an open quantum system with like open system, then you don't need to like put every time the charge current to be 0, right?
No, you have. I mean, you are in an open circuit. This is something that Giazzotto stressed a lot. He has a couple of papers with Bergeret and these guys. I mean, you're in an open quantum system. Sorry, in an open circuit configuration, meaning that the current through your device should be 0 when you apply the thermal current. And it's very important to compute your heat currents at the thermal voltage that makes the electrical current to the system equal to 0. So it's not a characteristic of our system. It's the way experimentally you have to do this, because I mean you really have to put the system to counterbalance the system with that thermal voltage to make the current equal to 0. Otherwise, you have an electrical current to use. Yes. Thank you for pointing out, because yeah, this is very
well, and that's how you compute the Seebeck effect. The Seebeck effect is basically your thermal voltage divided by your temperature gradient at no current.
Exactly. Experiment is what you do.
But many of the thermal rectification will be just calculate the heat current flowing through one branch to the other one in the reverse condition, right? And divide those, and then without taking into account the charge current. And I think if you think of a qubit, then charge current doesn't make a lot of sense there, because like heat transfer.
But let's discuss it.
For quantum dots, it's I think
okay, we can discuss this a little better. The last thing that I was mentioning, is this threshold, this trade-off between rectification and current, and I show you. I mean, even we can obtain a reasonable rectification factor, even obtaining good magnitudes for the heat current. This with this, let me just go rapidly through the conclusions. In this presentation, I talked about this hybrid normal superconducting Aharonov-Bohm system, and I hope I convinced you that putting together, the physics of interferential mechanism of the Aharonov-Bohm system with the superconducting property of the superconducting lead, you can really realize a multitasking and versatile quantum thermal system, which exhibit indeed very high and sizable Seebeck coefficient in the linear response regime, that exhibit also very high efficiency in the nonlinear response regime of the order of 55% efficiency, and this system can also be used as a heat rectifier, attaining 350% of rectification in the optimal case. Let me stress also that Francesco Giazzotto and his group at NEST in Pisa, they are really implementing the systems. And as far as I know, they got the samples for the simple normal case, and also with the superconducting lead too. And they are obtaining the first measurements. And so we will see if our prediction will be verified or not. So with that, I really say thank you for your attention. And of course, if there are other questions.
So it was was very clear to me that adding the ring greatly enhanced your thermoelectric response. However, I didn't get a simple physical reason for why. So if I think about just a Aharonov-Bohm ring, and I have just say simple voltage, I look at electrical current. As I thread that flux through the loop, I get a characteristic sinusoidal pattern of current versus flux. And so I imagine something similar happens with the heat current. So could you give us a simple physical picture about why this ring suddenly dramatically enhances the thermoelectric response?
I can give you a simple description instead of talking about the Aharonov-Bohm ring, but talking for Josephson junction, because I did it explicitly. The physics is the same, it's interference. What happens is that if you compute the transmission going left to right, summing all the possible paths you can have, this is different with the probability going from right to left only if you have this, you add this phase. What happens is that you have, if there is no phase, there is always a coherent, how you say, destructions of waves. Instead, when you add this difference in the dynamical phase acquired by electrons, which is tuned by the Josephson bias in the case of Josephson junction, but it's the same as the magnetic flux in the AB ring, you're shifting, the electrons waves versus the whole waves in one way from left to right, and in the other way from right to left. And what you can show is that you really have a current and a net current, so a thermoelectric effect going through your system. This is almost the physics there. Yeah.
Yeah, I think I missed, but when you said that you could achieve a rectification of 350%, what determines the highest possible rectification?
Well, I optimized it numerically. I know for sure that you need to have a finite flux and a finite electrostatic gate on the arm to get this high rectification. And however, independently on the parameters, let's say that in the case of the superconducting regime, so when T cold is very, very, very small, you almost obtain this very high rectification. It's not of the order of a 4 or 4.5, which corresponds to this 300, but it's pretty big. At least it's bigger than 100%. But of course, the system is highly nonlinear, and so really changing the parameters of your junction, the parameters of your system, you can get whatever result. But it's good that you can control it. So basically, you're controlling parameter. Once you have the sample, you control your external parameter, and for sure you get good rectifications.
Yeah. One other thing I think you see here is that if you have very small current, generally you have like very large rectification, like diverges in other systems, right? Which I don't think you see here. Do you?
Indeed. I mean, you're referring to this. Indeed, when the rectification is maximal, you have very, very small heat current. Indeed, you are.
There's nothing diverging, right? It's not like.
Nothing there. But indeed, because you're exploiting the real superconducting nature of the superconductor, heat fluxes that are not so high. And indeed, the values of the heat current is pretty small.
I have one more question. Can you go to the power plots? I didn't really distinguish between the colors, like what's happening there.
Yeah, actually, it's just different plots for different values of the electrostatic potential. The shapes, I mean, really are really wild. They really changed a lot. But here, the thing that the important thing that we want to describe is that really by changing these parameters, you can change arbitrarily these performance quantifiers. Yeah. Here, I mean, at least in principle, you can notice that the phase and the electrostatic potential acts in two different ways, because the phase, lets you acquire plus phi if you're going one direction and minus phi if you're going in the other direction. So it's a collective phase. Vg instead is just acquired on one arm, and so the phi depends on the differential mode. Vg is just does not depend on the differential mode. I mean, they act differently on your system, and you can tune these two quantities to enhance your figure of merit. Here is the power, for example, but also you can tune the efficiency, and it's really parameter dependent. You see, for example, for zero values. I mean, what is for Vg for high Vg, you have the best efficiency. Otherwise, if you change it, the efficiency completely go down. But then it really depends on the phase, because if you swap the phase again, you get better results.
And Vg is just the gate voltage.
Indeed. It's just an extra dynamical phase that they acquire. Basically, Vg times the length of the lower arm is the extra phase that you take if only you go through the lower arm.
So I would have thought that if you had no flux and no Vg, you would get no response. But I think you do, though.
Yeah, but again, because the nonlinearity of the system. Because of here we are really in the nonlinear response regime. Yeah. Basically, what I learned is when you are in the nonlinear response regime, you get almost all the results that you want.
Okay. Any other questions?
Do we have questions in Zoom?
Any Zoom questions?
Okay. If not, let's thank Gianmichele again.
Thank you.